This is the lecture over Chapter 5. It's going to be the second part of X-ray production, and we're going to take a look at what's going on whenever the electrons are accelerated across the voltage in the tube and strike the target, what all can happen, and what's going to be, how can we describe the phenomenon that happens after the electron encounters the atoms that are in the target. All right, so you can see here, the electron is going to strike the target in an X-ray tube. It's going to interact. You've only got two entities that the electron can interact with. It's got the atomic electrons or the atomic nucleus. It makes, a note here about interacting with individual nucleons, but we're not going to worry about that. So when the electron interacts with atomic electrons, you've got two broad categories of what can happen. Outer shell electrons can be excited to higher level energy states, and they will subsequently drop back to their original state and emit a low energy photon in the process. They get absorbed quickly in the material, and the energy will be converted into the random motions of the target, or in other words, heat. Another possibility is that the outer shell electron can be ejected. The ejected electron will move through the target material, may collide with other atoms, giving up some of its energy to the random motion of the atoms. Well, that's heat. Eventually, it'll find another atom that is missing an outer shell electron, and basically it's a guy looking for a vacancy in a hotel. The vacancy is there, so the electron just takes up residence there, and boom, it's no longer free. The energy is going to be ultimately absorbed, contributing once again to heat. Now, occasionally a high energy bombarding electron will eject an inner shell electron, either in the K or the L. There will be a vacancy that will be filled by the outer shell electrons dropping down, almost like, having a desirable apartment being desired by tenants of a less desirable apartment. They're going to gravitate towards that. Costs less energy, so boom, that's what's going to happen. The inner shell electrons are very tightly bound, and the energy released when the outer shell's electrons drop down will be high, particularly for a material with high atomic number. Many of these photons emitted in the downward cascade will be sufficiently high energy to be classified as X-rays. Some of the higher energy X-rays may be able to escape from the target without being absorbed. These X-rays will have distinct energies because there are distinct energy levels, and in order to get from one to another, it's quantized. And so for different atoms, it's going to be different values. These values are characteristic of the atomic species for which they are emitted and unique for each element. That's how we can tell what it is. And you can see here the graphs or the diagrams, the figures in this chapter are going to say much more than just the verbal description. So if you look at the diagrams, you can kind of tell what's going on. So here you've got a high level electron that's coming in, interacting with a K shell electron. That leaves a vacancy. In order to keep the atom more stable, somebody from the L or the M shell may very well jump down. It could jump from M to K, could jump from just L to K, and then something jump from M to L. When they do that, they release these photons. These are the characteristic X-rays that are being discussed. So now you've had a spectrum, a line spectrum, from transitions to the K shell in tungsten. This is going to be the number of photons per unit energy. This is going to be the energy. When they jump from the L shell, you'll see this amount of energy is what's being released. And there's no, that's what it is. It's quantized. There's not a spectrum there. And you're going to find that jumping from the L shell down to the K shell is going to be far more of what you observe than jumping from the M shell or jumping from the N and O. And that's what this particular table is trying to tell you. When you transition from the L this is the energy you're going to have. This is the relative number of photons. When you go from M, this is the relative number of photons. N and O, you'll see it's very unlikely that that will happen. If it does, this is going to be the energy that's associated with it. You do have something here about X-ray fluorescence and the emission of characteristic X-rays is sometimes called X-ray fluorescence. So this is saying essentially the probability of having an electron from an outer shell jump down to the K shell is far more likely from the shell that's just right above it, quote unquote, than it is from any of the other outlying shells. So only a small fraction of the bombarding electron energy appears in the form of characteristic X-rays. Most of it is dissipated either as heat or as bremsstrahlung. So that's what we're going to look at now. We've looked at the idea of an electron going in and interacting with another electron, knocking it out. What happens if it just gets close when it's speeding from the cathode over to the anode? So if it passes close enough, it'll interact with the nucleus. It's going at a particular rate. It sees the nucleus. It gets accelerated in that direction. Now, if a charge is being accelerated like that, you're going to see a particular wavelength that is released with that particular type of activity. And that's what the term bremsstrahlung is talking about. When the electron goes by, the nucleus causes the change in the path. When the change in the path happens, it must mean that a photon is being released. This is to make sure that conservation of energy principles are upheld in this particular process. You can think of it that way. Now, the initial kinetic energy of the electron as it enters the target, in other words, it's released from the cathode, goes over, and is about to hit the target there at the anode, the initial amount of energy that it's got is T sub naught. The energy lost by the electron is going to be delta T. It may just lose part of it. It could lose all of it. But whatever that loss is going to be the change in that energy, or delta T. And the photon energy, that sucker right there, is going to be h nu, which is the same thing as h times the speed of light divided by the wavelength. Or in other words, the change in the energy is going to be hc divided by lambda. Usually in any one encounter with a nucleus, an electron loses only a fraction of the energy. It may have other encounters with nuclei before losing all of its kinetic energy, and therefore any given electron may emit many bremsstrahlung photons. So it's not just a one-time deal in most cases. The electrons that strike the target may have an energy that varies with time if the voltage across the tube varies with time. So let us denote the maximum kinetic energy of the electron striking the target as T naught max. The numerical value of T naught max at KeV is the same as the numerical value. In other words, let's say I had 10 KeV, then that 10 value, not the unit itself, but that 10 value is going to be the same numerical value as the kilovolts peak. So you're not saying that those two quantities are equal to each other, because it's like saying 5 meters is equal to 5 newtons of force. You can't say that. And that's what it's trying to say here, is that the units of measurement are different, but the actual numerical magnitude of what's going on is the same. So the maximum possible X-ray photon energy emitted as bremsstrahlung will be provided by electrons, be produced by electrons that strike the target with maximum kinetic energy and come to rest in a single interaction. So in other words, the highest energy photon that you're going to see is if that electron is pulled by the nucleus and then just stops. So that would mean that the T naught max is equal to hc divided by lambda min. Now you might be kind of wondering, well, what do you mean here? In other words, if this energy was a little bit less, then that means this volume over here would be a little bit less. And the only way to decrease that is to increase the denominator. Once you increase the denominator, that would mean you're dividing by a bigger number, which would mean you would have less energy. So if you're looking at the maximum amount of energy, you've got to figure out what wavelength is going to be the smallest in order to make this computation equal. So the value of the minimum possible wavelength can be expressed in nanometers. Basically, you change a few things around here and you come up with the lambda min is 1.24 nanometers divided by the kilovolts peak. Now, X-rays produced by Bremsstrahlung can have any energy between 0 and T naught max. And that's in contrast to the characteristic X-rays. The characteristic X-rays, remember, is when the electron jumps from one shell to the next. Now, when it does that, there's only a specific discrete value that is produced. And you're not going to see a spectrum. But in Bremsstrahlung, you don't know exactly how this electron is decelerating. So it could be any number of different factors that would cause any number of energetic X-rays to be produced. It's all over the spectrum. That's why they call this a spectrum. So in an X-ray target, both Bremsstrahlung and characteristic X-rays production do occur. The X-ray spectrum produced by both is going to be shown here. The horizontal axis here is going to be the photon energy, and the vertical axis is going to be the number of photons per unit energy interval. So the number of photons emitted over some energy interval is simply the area under the curve. We're not really that concerned with that. This is going to be showing both filtered and unfiltered Bremsstrahlung and characteristic X-rays. The filtered spectrum results from preferential absorption of low energy photons as the X-rays escape from the target material. In other words, these X-rays can't get out, they're stopped. If they were unfiltered, you would see quite a bit of them. But in a filtered environment, you're not going to see those because they're stopped. So the maximum photon energy corresponds to the KVP. In a real target, some X-rays will be absorbed before they can escape, so that's why you see the lowest there. The lowest, this is called self-filtration or inherent filtration. In other words, there's not really much you can do about it. It's just because this is the way the apparatus is built. So note that the X-rays must also escape from the tube. Some may be absorbed in the window. The filtered spectrum follows the unfiltered spectrum at high energy because the high energy photons have little difficulty escaping. In other words, it's hard to go back to this. At these energies up here, it's hard to filter those out. Just through just the apparatus itself. At very low energies, no photons are able to escape. The average energy of the X-rays in the continuous self-filtration spectrum is much less than the maximum energy, and it's usually around 1/3. So, as you change parameters, what happens to the X-ray spectrum that's being produced? You've got parameters such as tube current, voltage, target material, and filtration directly, deliberately added into the beam. So let's take a look at this. This is going to be the effect of changing the tube current on the X-ray emission spectrum. So this reflects 200 MA, this reflects 400 MA. They both start and stop at pretty much the same spots. And the reason is the current, as it is doubled in this particular case, is only going to change the number of electrons that are coming to hit the target. They're not going to change any other, the voltage is not being changed. So you're not going to see any change here in terms of the energy spectrum of these X-rays. You will see a change in the number because you've got twice as many coming through at 400 as opposed to 200. But in terms of how that looks, it's going to have the same basic shape. It's just you're looking at a larger amplitude between the two. And that's what those paragraphs up there discuss. The voltage does strongly affect the amplitude of the spectrum. You don't expect the spectrum provided, the characteristic spectrum divided that the bomb. Let's try this again. We do not expect it to affect the characteristic spectrum volume, provided that the bombarding electrons have sufficient energy to eject inner shell electrons. The effect of increasing the KVP is going to be shown here. So you've got the X-ray energy just like what you had before. And you've got the number of X-rays per unit just like what you had before. Let's just kind of go back to that and just look at it. Though the X and the Y axes are the same. So rather than change the current, in this particular case, we're going to change the voltage, or the kilovolts peak. And when you do that, what do you notice? As that goes up, you're noticing that the X-ray energy actually begins to broaden out. You're seeing the peak also increase as well. And that's what that graph is trying to tell you. If the target material is going to be changed, we'll look here at that, see what kind of an effect that has. So again, the axes are the same. You're seeing here there's molybdenum with a Z value of 42, there's tungsten, and then there's gold. And you can see how the numbers here change. The higher the Z value, the greater number of X-rays per unit energy you're going to get. And here's another one. If you add in a little bit of filtration, how is this going to change? Well, if you add in just 2 millimeters of aluminum, you'll still see quite a number of X-rays being produced. You add in 4 millimeters, you're filtering out a lot of stuff that's going to end up that would be counted on this end. Obviously, you'll notice that it ends up pretty much at the same point here. Not as much over here on the high energy. What this is also doing is it's also shifting the peak to the right. So these are the graphical effects of what happens when you start influencing these particular factors. And the factors, again, are see if we can find them listed. I thought I had them listed here somewhere. Okay, can't quite seem to find it. But anyway, you can see how the characteristics change here as you look at the particular graphs. And these are important things to keep in mind. The effect of beam hardening is something that you may hear about in the clinic, and that refers to adding the filtration and reducing the overall intensity of the X-ray beam, but increasing the average energy. It's a beam hardening. So what's the efficiency? How much are we getting out for the energy that we're putting in? When electrons penetrate a thick X-ray target, they eventually lose all of their kinetic energy and come to rest. One mechanism of electron energy loss is Bremsstrahlung. All others of energy loss mechanisms, except for characteristic X-rays, in one way or another lead to heat production. So when you take a look at this particular graph, you're seeing the efficiency of Bremsstrahlung photon production as a function of the electron energy. Given two different elements, you're seeing how the efficiency which this is 1%, this is 10%. This is the electron energy down there. You can see how that changes. This is a logarithmic section down here as well as over here, so it's a logarithmic graph. You can see that at diagnostic energies, you're looking at about 1%. When you start getting up into the therapeutic, you're looking closer to 10%. And then if you're looking at 10 MeV, you're looking, closer to 40 or 50. So what is the directional dependence of Bremster lung? Um, let's take a look here at another graph. Again, the graphs here are going to show you a little bit more than I think the words will help explain, but I think the graph shows a lot. You're seeing a polar coordinate graph of the direction of the electron beam and then the direction of the photons as they undergo, as the process of Bremster lung occurs. You're seeing here with the low energies, in terms of the angle that is made with the incoming electron beam, you're looking at a pretty set of wide angles here of where this is going to happen. The distance from the origin represents the relative intensity of the Bremster lung. So the further you go out here, the more you're going to see at these particular angles. And you're seeing quite a bit of angular direction off of the low end of the KEV. The higher energies are going to point more and more forward. And it simply becomes they have more energy and, dealing with what they experience as they go through and interacting with the atoms. It's going to take far more energy than what an interaction with one nucleus is going to be in order to be able to stop it. So how is an X-ray beam attenuated, and how do we measure that? For a diagnostic X-ray application, a quantity that is directly proportional to the intensity is going to be called the exposure rate. Exposure rate is milliroentgens per hour, minute, what have you. And we'll get to what a Roentgen is later. So as an X-ray beam travels away from the source, its intensity can decrease by two particular mechanisms. One, you can see the beam spread out like this, and this is due to the inverse square law. In other words, as you come from a point source, you can see here at this distance, it's going to be, the entire beam is going to be contained within 4 particular squares. If you go another distance r out, you will see that that will now spread to 15 squares. So that's what happens when the beam starts to spread out as it's released from a point source. Another way it will spread out is the absorption and scattering in a medium. So as X-rays transverse matter, photons can be removed from the useful beam by absorption or scatter, and they can also be absorbed by matter, and the energy is converted to some other form. And you can see, as soon as I can get this to click. Well, I thought they had, I guess they don't have a diagram of it. Anyway, the absorption factor here, we'll get into that in just a little bit. So you see here, we'll have several problems here. I'm not asking you to remember this derivation. Just say that the intensity is inversely proportional to the distance squared. If you want to make it exact for a beam, you throw in a constant K and just say that it's equal. If you're measuring the intensity at 2 different spots of the same beam, the value K is going to be the same. You put the ratio of the two, you work through the math, and you find out that the ratio of the intensities is the same as the reverse or the reciprocal of those distances. And this is referred to as the inverse square law. Inverse square law is noted here in certain examples. If you work through the first one, you find that the output of a fluoroscopic X-ray unit is 10 milliroentgens per minute at a distance of 50 cm. What is the output at 75? Well, we know what the initial intensity is. We don't know what the final intensity is. That's what we're going to look for. We know what the distances are. Put them into the formula, solve for I2, and we have it. So now we talked about the beam, what alters an X-ray beam. We've talked about the inverse square law. Now we can talk about attenuation by matter. When photons travel through matter, some are removed from the beam, either by absorption or by scattering. So they're going through a particular, let's say a phantom, let's say they get absorbed and some get bent. So when a photon is absorbed, it disappears. It's not existing. When it's scattered, it is deflected and possibly outside of the beam that we are examining. So both of these result in a loss of intensity. So what we're going to do is we're going to take a source here and we're going to say it has one specific energy. It's not emitting a spectrum of energy. It's just one. As it's doing that, and let's say the beam gets collimated here. So we've got several of these pockets of energy here that are going through. They're going through a material here, which is going to interact with it, which is going to try to stop it. And then over here on the other side, we get a detector to figure out exactly how much we are going to receive. Here in this particular case, we're not going to concern ourselves with the beam spreading, just how much is attenuated. Now, we can expect the attenuation to follow an exponential relationship. So the intensity at some distance x through the material is going to be equal to what you started with times e to the minus mu x. Mu is going to be a linear attenuation coefficient. The higher this coefficient is, the more effective the material is at attenuating or attempting to stop the beam. So you can see here lead is 156 per centimeter. That's its linear attenuation coefficient. For water, for that same energy is 0.27 per centimeter. So lead is far more effective at stopping these things. This is also one of the reasons why we have lead shields when we go in and we get x-rayed at the dentist's office. Lead, it doesn't take that much lead in order to be able to stop these things. Whereas the amount of water that it would take, it's a little inconvenient at best. Plus, your clothes get wet. You don't want that. So the quantity here, I over I naught, represents the transmission. Transmission is going to be how much of the beam actually gets through, what's stopping it. The attenuation is basically going to be 100% minus whatever the transmission happens to be. If you ain't going through, you get stopped. That's how this is going to be looked at. So attenuation and transmission, if you add those two together, you should end up with the intensity that you had of the primary beam going through. Now, this only applies to monoenergetic beams. Once you start adding in other energies, things get a bit more complicated. You can go through and you can try to find an effective linear attenuation coefficient. Again, that's going to depend on what sort of energies you are using. In broad beam attenuation, some scattered radiation can reach the detector. The geometrical arrangement shown in figure 5.12, which is here. This is our geometrical arrangement. It is sometimes called a narrow beam or good geometry. In this arrangement, photons can be scattered out of the beam, but they cannot be scattered into the detector as they can in the case of broad beam geometry. And you can see here broad beam geometry. In other words, the detector, the size of the detector pales in comparison here to the height here of the intensity of the beam coming through. Sometimes it's possible to use an approximation formula here in order to be able to do it for broad beam geometry. If it's a polyenergetic, then you end up with even more problems. Okay, mean free path. Mean free path is going to be the average distance that a photon travels before interacting, either by scattering or absorption. It seems plausible that the mean free path is inversely related to the linear attenuation coefficient. In other words, the shorter the mean free path, the larger the attenuation coefficient. So if it takes you less, or if it takes more thickness in order for you to be able to have what we consider to be the average path of the beam, then the linear attenuation coefficient is not as strong. If your linear attenuation coefficient is very, very strong, beam's not going to go very far through there. So that's why there's an inverse relationship between the two. So the mean free path for 40 keV photons in lead, since you know the linear attenuation coefficient, you go ahead and put that in there. And that ain't very far. The half value layer is going to be the thickness of whatever the material is that is necessary to reduce the intensity of a radiation beam to half its incident value. This is the formula. If you've got the linear attenuation coefficient, you can figure out what the half value layer is. It's very much like the radioactive half-life. In other words, what's the half-life? Works very much along these same formulas. The second half value layer is the additional thickness necessary to reduce beam intensity by another factor of 2. For polyenergetic beam, it's going to become hardened. In other words, the weaker energies are going to be weeded out. And generally, your half value layer, their second half value layer is going to be greater than the first half value layer. Monoenergetic beam, there is no such hardening, so they're equal. So the energy distribution or beam quality of X-rays in a superficial or orthovoltage beam is often described in terms of the half value layer for aluminum. So it depends on the type of X-ray tube used, KVP, the amount of filtration, depending on the tube and all of these other factors. The superficial X-ray beam has an half value of 1 to 4 millimeters. So now, how can we confuse you further? We're going to talk about the mass attenuation coefficient. If you have different forms of the same substance, water, ice, and steam, and your incident beam is going to travel through that, the attenuation of it, it's not going to be anywhere near as attenuated as shortly here with steam as it would be with ice or particularly the form of water. So liquid water has a value here. It's a linear attenuation coefficient of 0.267 for 40 keV X-rays. For ice, it's a little smaller, 245. For steam, much smaller. This all comes back to the density of the material. Now, again, remember, all the materials are going to be the same. It's just in different forms. So how do we go about trying to calibrate the linear attenuation coefficient in order to be able to take that density into consideration? Well, if we take the linear attenuation coefficient and divide by the density, then we come up with something called the mass attenuation coefficient. This is independent of the physical state of the material. In other words, it'll describe the material no matter what phase it happens to be in. These are going to be the units for that. this is going to be a description of Rankin, very important individual, discovered a lot that really has helped your particular profession of radiation therapy blossom quite a bit. I would encourage you here to go through the summary. As a matter of fact, you might even consider reading the summary first. You may not understand all of it, but I have found that if you take the points as they are condensed and you look at it and you try to figure out what's going on, then when you go back and read it, you have at least some familiarity with what's going on, and it will help you to try to understand the material a little bit better. So, hope you got something out of this, and we will be going on to chapter 6 in the next lecture.